We are looking for all functions from the real numbers to the real numbers that satisfy this equation for all real values of x and y. In functional equations, a powerful strategy is to substitute specific values for the variables to uncover the function's fundamental properties. Let's label our governing equation as p of x, y. A natural first test is to set y equal to 0. Substituting y equals 0 throughout the equation gives us this. This simplifies to f of x squared equals x times the quantity f of x plus f of 0. Let's call this relation 1. Now, let's explore the symmetry by setting x equal to 0. Substituting x equals 0 yields this expression, which simplifies to ef of negative y squared equals negative y times f of 0 plus f of y. This is relation 2. Since this holds for any real number y, we can relabel the variable to x for easier comparison with relation 1. So we have f of negative xc squared equals negative x times the quantity f of 0 plus f of x. Now, let's compare. Notice the expression on the right-hand side of relation 1. We can see it is the same expression that appears, negated, in our second relation. This allows us to make a substitution. Substituting f of x squared in place of the expression in brackets reveals a crucial property. F of negative x squared equals negative f of x squared. Let's formalize this. Any non-negative number z can be written as x squared. So we have proven that f of negative z equals negative f of z for all non-negative z. But what about negative inputs? If z is negative, then negative z is positive. Our rule applies, giving f of z equals negative f of negative z, which is the same property. Since the property holds for all positive, negative, and 0 inputs, the function f is an odd function. This immediately tells us that f of 0 must be 0. Now that we've established f of 0 is 0, we can simplify our first relation, which will unlock the problem. We return to relation 1. We can now substitute our hard-won result that f of 0 is 0. The equation becomes f of x squared equals x times f of x plus 0. This gives us a beautifully simple identity. F of x squared equals x times f of x. This is the key to the solution. Let's return to the original equation, this time using the fact that f is an odd function. Here is our original equation again. Let's perform the substitution p of x, negative y. Replacing y with negative y gives us this new equation. We can simplify two terms here. Negative y squared is just y squared. And since f is odd, f of negative y becomes negative f of y. The substitution yields a second, different-looking expression for f of x squared minus y squared. We now have two distinct expressions for the exact same quantity. The only way this is possible is if the expressions themselves are equal. By equating the right-hand sides of our original equation and our newly derived one, we establish this equality. To find the relationship between f of x and f of y, we must expand both sides. Using the distributive property on both sides gives us this expanded equation. Let's simplify. We can subtract x times f of x from both sides. The equation simplifies slightly. Next, we can add y times f of y to both sides. This leads to a much cleaner relation. Now, let's gather all terms involving f of y on the left side by adding x times f of I to both sides. This gives us 2x times f of y minus y times f of x equals y times f of x. And let's gather terms with f of x on the right side by adding y times f of x to both sides. We now have 2x times f of y equals 2y times f of x. Dividing both sides by 2 reveals a beautifully symmetric relationship. Now, we must be careful. If we assume x and y are non-zero, we can divide to see that the ratio of f of x to x is constant. This means that for all non-zero x, the function must be of the form f of x equals a times x for some constant a. But does this formula hold for x equals 0? We proved earlier that f of 0 is 0. Our potential solution, f of x equals a times x, also gives 0 at x equals 0. So the formula holds for all real numbers. We've rigorously shown that the only possible solutions are linear functions through the origin. To be certain, we must verify this. We will substitute f of x equals a times x back into the original functional equation. The left side becomes a times the quantity x squared minus y squared, and the right side becomes x minus y times the quantity a times x plus a times y. On the right-hand side, we can factor out the constant a. This gives us a times the product of x minus y and x plus y. We recognize this product as the difference of squares identity, and this confirms that the left-hand side is indeed equal to the right-hand side. The solution is valid. The equality holds for any constant a. Therefore, the complete set of solutions is all functions of the form f of x equals a times x, where a is any real number. Thanks for watching. If you enjoyed this problem, give it a like and subscribe for more. See you next time.